Hello teachers, welcome back to Chapter 4, Section 4-3, and this is Part 2 of our video, and in this part we want to talk about the least common multiple. So I've got a problem here to generate this idea. Hot dogs are usually sold 10 to a package. My hot dog buns are usually sold 8 to a package. What is the least number of packages of each you must buy so that there's an equal number of hot dogs and buns? It says the number of hot dogs is a multiple of 10, while the number of buns is a multiple of 8. The number of hot dogs matches the number of buns whenever 10 and 8 have multiples in common. So let's make a list. Let's do this by hand to start with. Okay, so first of all, hot dogs are in multiples of 10. So multiples of 10, what do we mean by that? Well, 10, 20, 30, 40, 50, 60, we've got the pattern down, right? Okay, well, how about buns? Buns are in multiples of 8, so 8, 16, 32, 40, what's next? 48, and then 6 times 8, 7 times 8 is 56, 8 times 8 is 64, they keep going. Now, what are we really looking for? We're looking for the lowest value that is on both of our multiple lists, and if you scan your list, you see that 40 is the winner. So if we had 40 buns and 40 hot dogs, then we would have a matching set. So we would need to buy 4 packs of hot dogs and, did I do that right? And that should be 5 packs of buns, because you may have, well, noticed this, that I skipped one of our multiples of 8. There's a 24 in there. So that's 1, 2, 3, 4, 5 packs of buns and 4 packs of hot dogs. I'm sure you've seen that problem before. Typed up, it says this occurs at 40, 80, 120. The least of these multiples is 40. So we had common multiples. We didn't go that far in our list, but the least common multiple would be 40. So the same number of hot dogs and buns by buying 4 packages of hot dogs and 5 packages of buns. That takes us to a definition of the least common multiple. So the least common multiple, or LCM, of 2 non-zero whole numbers, notice it said non-zero, A and B, is the least non-zero whole number that is simultaneously a multiple of A and a multiple of B. And they show us visually with a number line method. So if you were introducing this to students, the number line method is a good visual way to handle this. You could also do this with rods. I'll show you a picture of that in just a minute. But we need our values to end at the same location. So if we're looking at the least common multiples for 3 and 4, so I stack my 3s up end to end, just like when we add on the number line, we're doing 3 plus 3 plus 3, no skipping spaces. And then we do the same thing with 4 plus 4 plus 4. Notice the endpoints do not line up until we get to 12 right here. They end in the same location at 12, and we can say 12 is the least common multiple of 3 and 4. You can also do this with colored rods. And so we have a 3 rod and a 4 rod. And if we were to stack those end to end, just like the arrows on the number line, you see the 3 rod is the green, and we have 4 of those, and then we have 3 of the purple 4 rods, and that stacks, they end in the same location when you get here. Notice everything lines up. And that gives us 12. Now, why did they put the orange at the bottom, the 10 rod and the 2 rod? Just to let you know that is a length of 12. Obviously, these are not the same length, so we're just trying to find where 4 and 3 size rods end in the same location, and that is 12. Now, the intersection method is what we did for the hot dog buns. So we can list all members of the set of positive multiples of the 2 integers, then find the set of all common multiples, and finally pick the least element in that set. We're not necessarily even having to find the set of all common multiples, right? If you get to the smallest number that is on both sets, you have found the least common multiple. So to find the least common multiple of 8 and 12, denote the sets of positive multiples of 8 and 12 by M8 and M12 respectively. If we do this by hand, here we go. So we have M8. Let's list all the multiples of 8. I promise I won't forget one this time. So 8's the first one. 8 times 2 is 16. 8 times 3 is 24. 8 times 4 is 32. 8 times 5 is 40. 8 times 6 is 48. 8 times 7 is 56. The question is, where do you stop? I'm going to put my ellipsis dots at the end here. This continues on forever, of course. I'm hoping my list is long enough. I just write out a few of them. Now let's look at all the multiples of 12. So 12 times 1 is 12. 12 times 2 is 24. 12 times 3 is 36. Now you might be going, hey, stop. I don't have time for all this, right? Because I have already found the result. The smallest number that is on both of these lists is 24. The least common multiple for 8 and 12 is actually 24. Do you see another multiple? Sure, 48. But we are going for the smallest. So we could say the least common multiple for 8 and 12 is equal to 24. And I'm going to show you, of course, the typed up version. So there's our list of multiples of 8. See, they took it out a little farther than we did. Our list for multiples of 12 also taken out farther than we did. They put arrows at the common factors. Of course, how many common factors do 8 and 12? I mean, common multiples. Let me use the right vocabulary. How many common multiples do 8 and 12 have? Well, it's infinite, right? They're going to continue to run and have common multiples. But we want the smallest, and that's the first one listed, which is 24. But it does show the intersection of the multiples of 8 and the multiples of 24. Again, notice the ellipsis dots, because even the multiples go on that are common to both lists go on forever. But you pick the smallest, and that is 24. Now, if your numbers are small, that's a reasonable way to go. If your numbers are large or not close together, then you might like the prime factorization method better. So here we go with the prime factorization method. To find the least common multiple of two non-zero whole numbers, first find the prime factorization of each number. Remember, we're good at this now. Prime factorization, you could use a factor tree, you could use the box method. Then take each of these primes that are factors of either of the given numbers. The least common multiple is the product of these primes, each raised, okay, each raised to the greatest power of the prime that occurs in either of the prime factorizations. Again, this is going to be easier seen than maybe reading the how-to. So here we go. We need to find the prime factorization for 2,520 and then again for 10,530. Remember, the tree method works great. It's a little bit sprawling sometimes. I see right off the bat that this would be 252 times 10. 252 you could divide in half to get 2 times 126. 2 is prime, 126 is definitely not. That could be 2 times, and that would be, what, 63? 2 is prime, 63 is not. 63 is 9 times 7 is prime. And then finally 3 times 3. Now we're not done with this tree, right? 10 breaks down into 2 times 5. But now we're finished. So I'm going to put this over here far to the right. Notice we have 1, 2, 3 2s, so that's 2 to the third. I have 2 3s, so that's 3 to the second, and I have a 5 and a 7. Now, y'all don't stop there, especially if you have a calculator nearby, although I encourage you to do a lot of this by hand. But what you really need to do is multiply that back out to make sure that really equals 2,520. So I have 8 times 9 times 5 times 7. Super fast. I'm going to check that. And that does give me 2,520. Okay? Now in pink, you do a factor tree for 10,530. Now again, my first thought is that factors into 1,053 times 10. 10 breaks down into 2 times 5. That's the end of that line. But this 10,053 is going to keep going for a while. Now, I know 2 does not divide into 1,053. I'm sorry, I said that wrong. But does 3? Well, we know it does, right? Divisibility test tells us that if we add each of the digits, 1 plus 0 plus 5 plus 3, and you get another number divisible by 3, then this number, 1,053, is also divisible by 3, and 1 plus 5 plus 3 gives me 9. As a matter of fact, it's divisible by 9. Let's use 9. So 1,053 divided by 9 is 117. Now 9 breaks down into 3 times 3. What about 117? And by the way, the 3 is the end of that line. Okay, so 117, I noticed right pretty quickly, 1 plus 1 is 2 plus 7 is 9. So 117 also divides by 9. So it's going to be 9 times 13. And 13 is prime. I'm glad we found that then. And then 9 breaks down into 3 times 3. So there's our completed factor tree. There's a lot of branches here. So we have 2. We only have one of those. But 3's we have 1, 2, 3, 4. So that's times 3 to the 4th. We have times 5. And then times 13. And again, I highly encourage you to check this if you have a calculator available. To check this on your calculator to make sure you have factored it properly. That is 10,530. Now, here's the good part. We want to find the prime factorization. Oh, we found it. I'm sorry. We want to find the least common multiple by including every number that shows up. So it doesn't have to be what's in common this time. It's every number that shows up to the highest power. So 2 shows up in both of these, but 2 to the 3rd is the highest power. 3 shows up in both, but 3 to the 4th is the highest power. 5 shows up in both, and 5 to the 1st, because it's 5 to the 1st in both. 7 to the 1st here, 7 to the 0 down here. In other words, it doesn't exist. It must be included. It doesn't have to be what's common. And then 13 shows up in the 10,530 factorization, but not in the 2,520. If we multiply all of this together, that is going to be our least common multiple. It looks like a pretty large number to me, but we're going to wait for the typed up version to get the final answer. So here's the typed up version for you. Overly simplified, by the way. 2,520, there's the prime factorization. 10,530, there's our prime factorization. Remember the trick again, is every single factor must appear, no matter which one it's in, to the highest power it shows up, which gives us 2 to the 3rd, 3 to the 4th, 5 times 7 times 13, which gives us 294,840. So those big numbers, you certainly don't want to make a list and find the intersection. You want to be able to use this prime factorization method. Here's an interesting theorem. For any two natural numbers, A and B, just like what we've been finding, the greatest common divisor, remember that's what we did, in the first video. So the greatest common divisor of AB times the least common multiple of AB. So again, remind you, I'm sorry, I had a cough a minute ago and I lost my train of thought. But the greatest common divisor is what we did in the first video. It's the largest number that divides both A and B. Whereas the least common multiple is what we just finished covering. And it is the smallest number that both A, B divide into. And if you multiply the greatest common divisor times the least common multiple, you're going to get the product of A and B. It's a very interesting formula. Now this problem asks us to find the least common multiple of 731,952. And then they go on with their result. It says, applying the Euclidean algorithm, we can determine that the greatest common divisor of 731 and 952 is 17. Okay, now I don't want to take that for granted. Let's actually apply the Euclidean algorithm for 731 and 952 and see if we get 17. So how do we do this? Remember, we divide the smaller one, 731, into 952. And we know that's just going to go one time, times 731, and we subtract. 2 minus 1 is 1, 5 minus 3 is 2, 9 minus 7 is 2. Do you remember what we do next? So we take the remainder now, and we turn that into the divisor, and then the dividend turns into, the divisor turns into the dividend. Now, how many times does 221 divide into 731? I would argue 3 times, because 3 times 221 is going to give me 663, and then I subtract. We could say 11 minus 3 is 8, and we borrowed right here, and we're going to have to borrow again. Remember, we're going to trade is what we call that. And then 12 minus 6 is 6. And so 68 appears to be, well, what would we do next, right? 68 turns into the divisor, and then 221 turns into the dividend, and we divide again. 68 divides into 221 3 times. 3 times 68 is 204. And I subtract 21 minus 4, and I get 17. So that 17 that they so quickly told us was the greatest common divisor using the Euclidean algorithm. There it is right there. Okay. Oh, we really didn't finish either, did we? We would have to divide 17 into 68. I jumped in there too quickly. 17 goes into 68. 4 times 17 is 68. Remainder 0. You have to have a remainder 0 to pull this off. So again, this is really what we're looking for. So finish up. Don't highlight too soon. I saw the 17 and thought we need to stop, but we were not finished there. So that 17 is that 17. Now, how could we use that information to find the least common multiple of 731 and 952? Well, remember, I'm going to write it on this page and then switch pages on you. At the top of the page, here I go. Remember, the greatest common divisor of 731 and 952 times the least common multiple of 731 and 952 is equal to 731 times 952. So we could substitute the greatest common divisor we've already found. So this is, all of this is 17 times, we don't know this, I'm going to call it x, is equal to, and then we can multiply 731 times 952. Let me do that now. I get 695,912. How would I solve for x? By dividing by 17. So we've got 40,936. So we've done this by hand. Again, I do have it typed up for you. So there's the 17 they told us before. This equation is exactly what I wrote down, but not so neat. That's 17, which is the greatest common divisor, times the least common multiple, which is what we're looking for, is equal to the product. Just multiply 731 times 952. And then we're going to divide that by 17. And we've got 40,936. And that was probably easier than prime factorization for each of those numbers. And remember how to find the least common multiple? It's the prime factors they have in common to the smallest exponent. I don't know. I think it went about as fast. So whatever you like better, or whatever's more convenient, or whatever gets you through the homework, right? But it's nice to know these different methods for working with greatest common divisor or greatest common factor and least common multiple. This is the last problem I had for you. If you have trouble with the homework, please reach out and let me know. Otherwise, I hope you have a fabulous day.